Hey everybody, this is my second time trying to record this, so I'm gonna try to be to the point and clear. And like I normally say, if you'd like to put it at 1.5 or double speed, feel free. This is what we started in class, analysis of functions. We're going to be able to find where it's increasing, decreasing, and concavity. So these are the notes we already did in class together. I added this picture of this spider teaching a math. The long story behind that one, and Rory had dropped this knowledge here in class that the second derivative could determine concavity. So it's concave up if the slopes of the tangent lines is increasing. Another way to say it, the first derivative is increasing, or the derivative, the rate of change of the derivative is greater than zero, or the second derivative is greater than zero. And by that same logic, we could say that f of x is concave down when f, the second derivative, is less than zero. And there's this other piece of information. I'm not writing it now because I already wrote it on the first time I tried to record the video, but a point at which f of x changes concavity is called an inflection point of f. So if you look right here, you see how it's going concave up, 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 getting steeper, bam, but then it starts getting less steep. So we would call this point right here an inflection point. And I have it underlined there. And here's just a quick visual example. Uh-oh. Oh man, it's being laggy. Uh-oh. Wow, that was ugly. Okay, well anyhow. So to summarize, sort of hopefully clearly, the things we just discussed. Well, we know at this point the derivative is positive on an interval. It's increasing on that interval. Positive slope. Less than zero, it's decreasing. But now we have also thrown in the mix second derivative. It would be concave up on that interval if it's greater than zero. Second derivative less than zero on an interval, concave down. So now, given this information, we could take a function and find the intervals on which that function is increasing, decreasing, concave up, and concave down, but also find the x values of any inflection points. And we'll show a quick example here how. My goal is to keep this quick. So find the domain of f. We're going to need to find the domain because we need to know if there are spots that we shouldn't necessarily consider because there's not even an output there. Find the first derivative and the second derivative functions of that function. Find all the values of x at which f prime of x and f double prime of x are either 0 or do not exist. Those are the only values of x at which the first derivative or the second derivative might change sign. Only at 0 or does not exist. And let me show you why visually. Well, here, look, the first derivative is 0. It flattens out. And there it changes from decreasing to increasing. So one thing I remember being confused about, it doesn't necessarily mean that at 0 or does not exist that you'll have these things, but those are the spots we should check. So here you can see it goes from decreasing to increasing. Here, this goes increasing to decreasing, and here the derivative would not exist because of this cusp. And now we're going down here, bada bing, bada boom. Once again here, it gets flat for an instant. The derivative would be 0, but be careful because here the derivative doesn't actually change signs. It's just for an instant it's flat, but then it still is decreasing the whole time. So we still would say that the f prime doesn't change here, even if at that one moment it's 0. So that would be one spot we could check and see, oh, it's actually not a spot where, but it is a spot where it goes from concave up to concave down. And then here the derivative actually wouldn't exist because it's momentarily vertical. Can't get a vertical slope. So if you calculate the derivative at that point, it wouldn't exist. And so the strategy that we're going to do, we talked about strategy here. ensure all these things. And then once we found those values of x, what we could do is do sign tests on the number line. Draw a number line, label the value x values on there, then test the signs around those x values. I'm going to do a quick example, try to keep it quick, not take up too much of your day, and not talk for too long. It's also nighttime where I'm at, and I think I should hit the sack soon. Oh man. Okay, so we're just going to do one example. I put an S for the future honors calc. Alright, so this is a nice polynomial. Anytime we have a polynomial, the nice thing is we know the domain is all real numbers. Negative infinity to positive infinity, we could say. Okay, the derivative, oh, this is going to be nice. Just power rule this. Don't have to worry about any of that chain ruler sins we've been doing. Okay, so, and also, this is another polynomial, so the derivative also exists everywhere. I got my steps over here on my other screen so I can show you. What we're doing is find the domain of f, find first derivative, and I just made sure to notate that because it's not going to have any does not exist. So let's jump in with this. Let's set this equal to 0. Since it exists everywhere, we could try to find where are the spots that equal 0. So we'll take that and set that equal to 0. We got 4x cubed minus 6x squared equals 0. Oh, this isn't too bad. I could factor this 2x squared out. I would get 2x minus 3 equals 0. So, oh, actually not too bad. I could then just say, well, x squared could be 0 by the ZPP, or 2x squared, you might say. So x could be 0. And then 2x minus 3 could also be 0, which would give me x to be 3 halves. So these two values are the only values where the first derivative might change sign. And the key word is there, might. That's why we're going to have to test them. So it might change sign. So let me scroll down and let's look at the sign test. So we're talking about the sign of the first derivative. And the two values we are going to test here are 0 and 3 halves. I don't know if, I thought some people said you had done this last year. I don't know. So, and then below I'll say, okay, I can notate whether it's increasing or decreasing. So let's test this out. Okay, so I've got f prime of x equals 2x squared times 2x minus 3. So this is always going to be positive because it's 2x squared. But let's try plugging in some of these values around it. So maybe I'll try -1 first, because I want to find out what is happening up until that 0 value, right? I'm going to test values around it. So f prime of -1, this will be a positive. This is always going to be positive times a negative. So it's going to be less than 0. So it's negative on this part. And we have to change colors, which means it's decreasing. Okay. Now let's try a value in between. So this is 1.5. So let's try 1. F prime of 1. That's going to be a positive. And a negative, which has 2 minus 3. So still less than 0. So that is actually not a spot where it's going to be And then lastly, we got, let's use 2. We've got f prime of 2 equals positive. This will now be positive. So we can see that that would be the only point here at which, now it's, let me do different color, it's increasing. So what we could say is that it's going to be increasing from 3.2, or sorry, not 3.2, 3 halves to infinity, and it's decreasing the rest of the time. So it gives me a strategy to analyze my function. I could also, of course, analyze it a bit more using my second derivative, but notice the video is getting long, so I'm just going to pause here and call it a day for everybody. Hope this shows you a little bit how the derivative can be used to find some key aspects where the function may be changing. And we'll talk a bit more next week about looking at finding these inflection points and changes in concavity. Much love, everybody. Have a nice weekend.